Hi, everybody. Welcome back to Dave's Math channel. Today I'm going to feature another daily math problem. I posted this one a couple days ago on the Facebook group Classical Mathematics. And this involves two kind of idealized free fall periods. One, the period of a satellite orbiting the Earth, but orbiting just barely above the surface of the Earth, assuming there's no atmosphere. And the second, which is even more idealized, I think, involving the time it takes for a object to fall through a evacuated tunnel going directly through the center of the Earth, as shown on the right. So anyway, these are the problems we're gonna solve today. So let's get started. So here's the problem statement written out specifically. So first, I tell you what the mass of the Earth is approximately, because we need that. It's about 5.972 times 10 to the 24th kilograms. That's a lot of mass. And the radius is approximately 6,371 kilometers, or if you like, 6.371 times 10 to the 6 meters. So anyway, we need that. And then for part A, I'm asking what the period of a satellite, like I said, an idealized satellite orbit with an altitude of 0. Of course, you'd have to get rid of the Earth's atmosphere in order to make that work. But, it is an idealization. Um, and we also need the strength of Newton's gravitational constant, which is given by the letter capital G, whose value is approximately 6.6743 times 10 to the minus 11 meters cubed per kilogram per second squared. So we're going to need that, actually for both parts. And then for part B, I'm asking for how the time it takes for an object to fall through this tunnel, fall all the way through this tunnel to the other side of the Earth. Um, assuming there's no air resistance. So anyway, so let's solve part A first. These are sort of two different kind of problems, it looks like. Actually, we're going to see the solutions are very closely related, which might not be obvious. But anyway, let's solve part A first. I think this is the easier one. Usually, students learn this, I think, their freshman year of college physics. You learn how to solve problems like this. You don't even need calculus for this, really. I mean, you're just applying Newton's law. In Newton's law of universal gravitation says that the gravitational force acting on any object due to the Earth is equal to capital G times capital M, that's the mass of the Earth, times little m, that's the mass of the object, divided by r squared, capital R squared, where in this case capital R is the radius of the Earth. That's just the gravitational force at the surface of the Earth. I'm sure you guys all learned that formula if you took a class in first year physics. And for a satellite with a radius of that orbit, it's a circular orbit. So the gravity, the gravitational force, results in the centripetal force. That's the force, the acceleration force that's keeping the satellite in orbit. It's falling, but it's falling in a circle, and the force that's making it fall is gravity, and its magnitude is mv squared over r. That's a well-known formula. The centripetal force required to pull in any object to keep it moving in a circle is equal to mv squared over r, where v is its orbital velocity, or its orbital speed, if you like. And now we just have to do a little bit of algebra to solve for the speed. And it turns out to be equal to the square root of the fraction g times m divided by r. That's not too hard to derive. So, but we still have more work to do. That's the orbital speed. We still we have to calculate the period, which I'm calling t sub o for orbital period. So, we just use the formula distance equals velocity times time. And if the time's a full period, that means the distance the satellite's traveling is 2 pi r, 2 pi capital R. So we have 2 pi capital R equals v times t sub 0. And now we can just do some more algebra to solve for t sub 0, or t sub o, T sub O is 2 pi r over v, and we already know what v is. It's square root of gm over r. So when we plug everything in, we get 2 pi times the square root of r cubed over gm. We put the r inside the square root, so it becomes r cubed inside the square root. There's already a factor of r right there. So now we just have to plug in the numbers. And when you do that, you can cancel out the units. You don't even have to write the units as long as you're using using SI units, standard international metric units. You don't have to write them all down. I did it here anyway. But when you're done, you'll find that the orbital period is approximately 5,061 seconds. Seconds a metric unit of time. And if you translate that into hours, minutes, and seconds, you get 1 hour, 24 minutes, and 21 seconds. So that's the orbital period of the satellite. And actually, this isn't that much of a generalization or an idealization because, there are satellites orbiting the Earth. Low Earth orbit, I think, is defined as somewhere between 100 and 1,200 miles. And 100 miles is a pretty low orbit. I mean, I guess technically that is outer space. There's practically no atmosphere at that altitude. And I think for a satellite of that altitude, its orbital period is about 90 minutes. So it's not that much longer. Um, so anyway, so I point that out. But now, what about part B? Part B is trickier. So for part B, we want to calculate the time it takes for an object to fall all the way through the Earth. And we're making a couple assumptions. Actually, I didn't tell you what the other assumption is. I probably should have told you. We're assuming that the Earth has constant density, which it doesn't. But this problem's a lot easier if you make that assumption. The Earth is a lot denser at its core than it is, near the surface. That's just because the core consists of compressed iron and nickel, whereas the soil near the surface, the crust, is mostly just silicon and oxygen compounds. Has a density of about 3 grams per cubic centimeter, whereas the core is about 10 or 11. So there's a big difference. But we're making an idealization here. We're assuming that the Earth has constant density. And if we assume that, we still have to calculate. The first thing we have to do, this does require calculus, by the way. But it turns out the calculus isn't that difficult. And anyway, I'm just going to show you how to do this calculation. So the first thing we have to do is we have to calculate the acceleration due to gravity of acting on this object that's falling through this hole going through the Earth. And, you might think that it's always GM over R squared. That's not true. That's only true if you're above the surface of the Earth. You probably know the inverse square law. The gravitational force acting on an object is inversely proportional to the square of the distance from the Earth's center. That's only true if you're outside the Earth. It turns out if you're inside the Earth, it's not the whole Earth that the gravitational force. I mean, parts of the Earth are pulling it up because there's parts of the Earth that are farther from the center than you. Those parts are kind of pulling the object up. And if you do the calculation in the right way, you can use Gauss's law. I'm not going to do that here, but it turns out that the gravity has the same form as the force, electrostatic force, for which we often use Gauss's law in electrostatics. And from Gauss's law, it turns out that the acceleration due to gravity at a point, beneath the Earth's surface, if we say little r is the distance from the center of the Earth, which is less than big R, which is the radius of the Earth, then it turns out we have we have kind of the same form for the acceleration, except instead of capital M, instead of the mass of the entire Earth, we're using the mass of the portion of the Earth, which I can call little m of r here. Little m of r is just the mass of the spherical portion of the Earth that's no farther than we are from the center. So it's kind of like a subsphere of the Earth, which gets smaller and smaller as we fall. It gets to size 0 by the time we're at the center of the Earth. Actually, it turns out that if you're at the center of the Earth, I don't know if you guys realize this, but if you're at the center of the Earth, you would be weightless. but your weight would, if the Earth had constant density, your weight would decrease linearly in linear proportion to how far you are from the center, which is kind of a neat fact, I think. Um, but anyway, um, so um, so we still have to calculate little m of r. Well, if the density is constant, then little m of r should be proportional to little r cubed. And I think it's pretty easy to see that it's equal to capital M times little r cubed over big R cubed. Because this is equal to capital M when little r equals big R. It's proportional to little r cubed. That's the only way it can have a proportionality. You can check for yourself. But anyway, so that's what we have here. And now we can combine these equations to get a differential equation for the equation of motion of the object as it falls through the earth. And, if you know a little bit of calculus, know that acceleration is the second derivative of your position, your displacement. So I'm writing this r double prime. R double prime of t, and you have to have a minus sign here because the acceleration is downward. Acceleration is negative. Remember, r is decreasing. So we have r double prime of t is equal to minus g times capital M all over capital R cubed. That's what you get when you simplify, when you combine the two previous formulas. Solve for little m of r. That's the constant proportionality you get. And then you have to multiply all that by little r of t. I think you can see from these equations that the acceleration is directly proportional to the radius because little m of r is proportional to the cube of the radius, and then we have a factor of r squared in the denominator. That's going to give you an overall factor of r in the numerator. So anyway, you get this differential equation, but this is a very easy differential equation to solve. This is a differential equation you see a lot in physics. So it's one of the first ones you learn how to solve when you take a class in differential equations, which is usually second or third year calculus. So now we're getting into some pretty advanced calculus here, but this is a very simple differential equation. You see it a lot. And it turns out that this is a differential equation of a sine wave or a sinusoidal function, which has the general form a cosine omega t plus b sine omega t, or omega is what's called the angular frequency of a sine wave. It's really the ordinary frequency divided by 2 pi or multiplied by 2 pi. From this differential equation, we can see that omega is just the square root of this multiplicative factor in front of r, gm over r cubed. So that's the angular frequency, and it's useful to calculate the derivative of equation 1 with respect to time. That'll give you the velocity as a function of time, which has almost the same form. We have a factor of omega multiplying everything. It just comes from the chain rule. Now we're going to get inside these brackets. We're going to get b cosine omega t minus a sine omega t. If you do the calculus, you'll see that's what you get just by differentiating equation 1. So now we have these two equations, and we also know the initial condition. That's how we can solve for a and b. Because we know, for instance, that at time 0, the object is a distance capital R from the center of the Earth. That's kind of our initial condition for equation 1. If we plugged in t equals 0, we would get capital R equals capital A times the cosine of 0 plus capital B times the sine of 0. But you know that the cosine of 0 is 1 and the sine of 0 is 0, so you're going to get capital R is equal to A. So we know A now. A is capital R. And if we plugged in the initial condition for equation 2, we know the velocity, the speed of the object is 0 at time 0 because we're just dropping it in to the hole. We're not throwing it. So we have 0 equals omega times, in this case, b times 1, cosine of 0 plus minus a times 0. So you're going to get omega b. And that means that b equals 0 because omega is non-zero. So we got a equals r and b equals 0. And so we could just plug in those values of a and b to get the equation of motion of the falling object. It turns out it's R of t is equal to capital R times the cosine of omega t. I think this is a really neat equation. What this is saying is that if the Earth had uniform density and you threw an object into an evacuated tunnel that went all the way through the Earth, then it would undergo what's called simple harmonic motion. It would have the same motion as a spring, as a mass on a spring, or approximately like a pendulum, just a sinusoidal back and forth motion. And we know what omega is, so we can calculate the time it takes to fall because the time it takes to go from one end of the Earth to the other, that's half a period, right? A whole period would come back to where you started. This object that's falling through the Earth that's going to keep oscillating back and forth within this tunnel if there's no friction. After twice the time it takes to fall to the other end of the Earth, it's going to come back to where it started. It's going to fall back up. So, plugging in the value we know for omega, which is square root of gm over r cubed, we're just taking the reciprocal of that, multiplying it by pi here. So we get pi times the square root of r cubed over gm. But when I was solving part A, you might remember that the answer we got was twice that. We got 2 pi times the square root of r cubed over gm. So that says that the time it takes for this object to fall through the Earth is exactly half the time it takes for the satellite to orbit around the Earth. I think that's kind of neat. And what that means is if you do it a full period, so if you want to know how long it takes for the object to come back after you drop it through the tunnel, it would come back at exactly the same time as it would take for a satellite to orbit all the way around the Earth. So what that means is that if you had a satellite directly overhead, at the same time you drop the object into the tunnel, by the time the first of all, by the time the object went to the opposite end of the Earth, assuming that the satellite has the same trajectory, well, it has to because it's a great circle. But what that means is the satellite's going to be directly overhead by the time it comes to the opposite end of the Earth. Pretty amazing. They both end up in the same place, halfway around the world. And then, of course, they end up in the same place once it comes back. And that keeps repeating forever. So they have the same orbital frequency. I think this is really amazing. And I don't even know if I know an obvious kind of intuitive reason for this. But when I first learned this, I remember I learned this like the first year of calculus when I was learning physics. I actually solved a problem like this, and I was pretty amazed. I was pretty amazed by this fact. But it is true. So the time it takes for the object to follow the opposite of the Earth is half of what we calculated before, which is approximately 2,530 seconds, or approximately 42 minutes and 10 seconds. So that completes this daily math problem, my solution to this daily math problem, which I think is a pretty neat problem. So anyway, thank you for watching. Long live math, and I'll see you guys next time.